what we are trying to figure out is to obtain a relativistic wave equation or a wave equation for a relativistic particle, okay, in quantum domain, or a, okay. So the first equation what we will see, so these are the historic notes I am going through, okay. Then once we will do the quantum field theory, when we try to quantize different kinds of fields, we will see these equations emerge itself as the field equations, okay. So let's start with a free particle, okay. What is the energy momentum relation of a free particle? Okay, everything we will be doing with the free particle. Okay. So what is the energy momentum relation? So E square is equal to E square C square plus M square C square. Clear? Okay. So this I can write as E square by C square minus B square equal to M square C square. Okay. Okay. Now, if you are now, let's try to. So you are having energy as an observable quantity. Okay. Momentum is an observable quantity from the second postulate of the quantum mechanics. So you can write all the observables as operators. Clear? Okay, let's try to naively put these operators there. Okay, what I mean by that? So from quantum mechanics, I can use this energy as an operator, I cross partial by partial t, and momentum as minus I cross nebula. Is it? So if you try to quantize a theory in quantum mechanics, let's say you are having a particle moving, okay, and you try to quantize its motion. What happens? How you quantize it? You just raise the observable quantities to the operator level. Clear? So this energy is an observable quantity, and you put for that as an operator. Okay. So that we call as a Hamiltonian operator, if you remember. Okay. So this we call as a momentum operator. True? Clear? Okay, so we are doing directly, we are just picking up the concepts of the quantum mechanics and using them in this very equation. Clear? Okay?
Yes, sir.
Okay. So this is just a direct way to do it. So now let's put for this E square, what will be E square? So you are having this 1 by C square, it will be simply minus H square, okay, partial partial T2, okay, then minus, what is P now?
I.
So
H cut square nebula square.
So it is minus H square nebula square, okay. Okay. So when you try to quantize this, okay, so you introduce a wave function. Let's call that wave function as phi, okay, is equal to M square C square. Clear? Because operator has to act on some function. Okay, so this is a wave function corresponding to the particle represented by this energy momentum relation. Okay, so here is an important assumption. So since we are doing, okay, we are considering a free particle, it is having no spin at all, it is a zero spin particle. Is there any spin we have considered?
So
No.
Plus here P.
Hmm?
P square plus I.
No, look here. So it is
I square is
square,
minus.
so minus,
Minus,
plus,
plus.
and I square is minus. Okay, so minus H square nebula square. Okay, so minus and minus will be plus. Clear? Got it?
Onun minus to the formula.
Where?
Okay.
That's okay.
Minus can be square.
So what I am saying, so we are considering a free particle which does not have a spin. Okay, it's a spin zero particle. Such particles we call as scalar particles. For corresponding to that, I am writing a wave function phi, because once I put it into the operator form, the operator has to act on a wave function which represents such kind of particles. Clear? Got it? Okay. So now let's write it. So it will be 1 by c square partial 2 by partial t2 minus nebula square acting on this phi is equal to minus m square c square rather divided by h cross square acting on phi. Clear? Okay. Yes. You take minus out. You take one minus out. Minus is here. Minus is here. You take it out and put it here. So it is like this. So I will write now this box operator, and you take this on the other hand side, m square c square by h cross square acting on phi it is equal to 0. So this equation is known as Klein Gorden equation. Although this equation was first derived by Schrodinger himself. Schrodinger was looking for a wave equation of relative particles that satisfied de Broglie's hypothesis. Okay? It is actually the Schrodinger who derived this kind of equation. Later on it was derived by Klein and Gorden, okay, in the different context, but actually it was, and Schrodinger discovered this kind of equation, and from this equation he put his famous Schrodinger equation. That we'll see in a moment. Okay. So we have arrived at, so this is a relativistic equation for a particle. Okay. Now we have, okay, we have actually here merged both relativity and quantum mechanics. Clear? Got it? You are having H here and C here. Both the terms are arising here. Okay. Now let's look whether this is a good equation to start with or not. Okay, whether it gives you the physically relevant solution or the physical solutions or not, whether it has some unphysicalness. Okay, so let's try to figure out, let's try to interpret this kind of equation, okay, what it yields. Okay. Okay, now since it's a free equation for a free particle, so free particles are represented by the plane waves. Okay, clear? So what is the solution of this very equation? It's a plane wave solution. Okay, so it admits, so this equation admits plane wave solutions. Let's try to figure out. Okay, how I write the plane wave? Okay, let's write this plane wave as sum A e raised power plus minus I this p dot x. Okay. So that's e raised power plus minus I. Okay, so it is et minus p dot x. So this is a plane wave. Clear? Okay, so let's put this phi in that equation, and let's try to figure out what we'll get. Okay, so before doing that, you know, okay, so we have a note here. So if I take the momentum operator, this p mu, let's act this on phi. Okay, so let me write what this momentum operator is. So momentum of anybody? So you are having this p mu. Okay, let me write p mu upper. So how we write it? It is E by C and vector p. Clear? So now this will go as a momentum operator. Let's write this as a momentum operator. How I will write it as? So it's 1 by C. So it will be IH trans partial by partial T. What about this thing? P will become as minus IH trans nebula. Clear? Okay. So what it will be? Let's take IH trans common from both. So it will be simply 1 by C partial by partial T. So it is minus nebula. Okay. So what this is the representation of which operator? Partial mu. Okay? Clear? So now let's take this P mu operator acting on phi. So that's IH trans partial mu. Okay? Acting on this phi. What is phi? A e raised power plus minus I. Okay, let's write P alpha x alpha because it's a dummy index. Clear? Got it? So now tell me what you will get. You will get, okay, so there is an extra sitting here. There is an extra, so okay, so what you will get? You will get simply this P mu number, okay, A P mu, because this partial mu will act on X, okay, this plus minus I, P mu will come down, okay, so you get plus, okay, so if it is plus, so you get like this, clear? So upper sign will be minus and lower will be plus, clear? So that means these plane waves are the eigenstates of the momentum operator, clear? So now let's substitute them in this very equation. Okay, so what I will get, what this box operator is, it's actually partial mu plus m square c square by extra square. Okay, what is our phi? It is a e raised for plus minus I. Let's say it's p alpha x alpha, that's equal to 0. Let's try to figure out what is the energy corresponding to this very particle. Okay, so now what will do this thing? Okay, this partial mu will act on this x, is it? What it will bring down? Let's take only one sign. Okay, let's take only one sign. It will be the same if you take minus sign, clear? So when partial mu acts on this x alpha, what it brings down? IP alpha, is it? So you will get from this partial mu IP mu, clear? Because the index here is what? Mu. It will be replaced by this index. Okay? Then this partial mu will act on again this thing. What you will get? IP mu. Clear? Okay? So plus m squared c squared, and there is sorry this extras which I always forget. So you are having extras and extras. So extra square, so that's equal to 0. Clear? Okay? So what you get? So it is minus p mu, that's equal to minus m square c square. What is this p mu? So it is actually, let's write it as p square minus this vector p square, that's equal to m square c square. Okay? Everybody followed it? Huh? So I have written, okay, I have written this p mu as this p naught and vector p. Clear? And p naught is what? E by c. So what you will get? So you will get this p square, that's equal to this p square plus m square c square. Or in other words, I can write what is p square? In terms of E, let's write in terms of E. So I will be having this P0 is equal to plus minus this EP. Okay? So let me write. Okay, or I can write this P square by C square is equal to P square plus M square C square, which implies E is what? Plus minus root of P square C square plus M square C raised by 4. Or in other words, I will put this P naught is equal to plus minus EP, and that's actually equal to plus minus root of P square C square plus. So this is just for the notation. EP I will be using frequently. Yeah? EP means this root factor. Clear? So now what you got? So back you have got the energy momentum relation of a free particle. Clear? So but here you are obtaining two values for energy. Although it was there in your energy momentum relation, it was there, but we are not bothering about that in classical dynamics. Okay, so here is a problem. Okay, so you are having positive energy solutions are okay, but you get actually a negative energy solution as well. So you are having a negative energy for a free particle. Clear? You got my point? So this is the first problem with the Klein Gorden equation. You arrive with the negative energy solution. What negative energy solution for a free particle means? Okay, so first thing is, okay, what you get? Negative energy solutions. Everything is with that. Okay, So you got these negative energies. So remember, it is a minus sign. Both signs are important. Clear? So in quantum mechanics, it is a very important point. But in classical domain, it doesn't matter. Okay? So what happens? Let's say you are having a particle. What will happen? So let's draw let's draw a rough diagram. Okay? So you can be having an energy on this side and momentum on this side. Okay? So you will be having one parabola here and another here, like this thing. So you will be having two branches kind of thing. Now what will happen? Let's say you are having a particle that starts with the arbitrary momentum. Clear? To lower down the energy, what will happen? So it will make a transition to the negative energy states. Okay? You got my point? Let's say you are having a particle that starts with a positive energy. Okay? And there are negative energy states available as well. Clear? You are getting my point?
Yes, sir.
So you start with a problem, okay, where you are having negative energy solutions as well. You are having available negative energy solutions as well. And a particle carries a positive energy. So what is the natural choice for the particle to go? So it will lower down its energy. Clear? So it will make a transition to the negative energy. Okay, to lower down the energy. Okay. Now what will happen? So what will happen? Lower negative energy is smaller than the upper negative energy. Let's say it goes to here at this very point. So it may drop to here because this is also the negative energy. Clear? So that means a particle which is having the infinitely available negative energy, all these kind of states, it will cascade down to those energy states, releasing an infinite amount of energy. Clear? So which is unphysical. So it will make matter unstable. You got it? So because you are momentum is a continuous variable. Okay, momentum eigenstates, it forms a continuum. For a free particle, it's a continuum. So you will be having all these energy states available, all these energy states on this line. So these are positive energies and these are negative energies. What will happen? A particle will move down. Okay, so ultimately it will go to the negative energy parts. So in all these kind of states, so it will release what? So once a particle makes a transition to the lower energy states, what happens? It releases a amount of energy. Clear? So it will continuously do that because these will be the lowest possible energy states. Okay, so the system will be completely unstable. Okay, if these negative energy states are available there, so the system will be unstable. Clear? Got it? So that means these negative energy solutions are a problem. Okay? Got it?
Yes, sir.
Okay. So what are its consequences? What these negative energy solutions have? Okay? What other consequences they pose? Let's try to figure out the continuity equation of this thing. Okay? Okay, so you can, there is one more point. You can, okay, so first let's figure out the continuity equation. Everybody followed it? Huh? Everybody followed it? Huh? If anybody is having a question? Anybody is having a question? Huh? Okay. So let's try to figure out the continuity equation. What the continuity equation gives you? Tell me. It gives you the interpretation of the probabilities. Okay, so you are having a continuity equation. So think of a continuity equation in electrostatics. So what does it mean? If a charge is enclosed within a volume, so change in the charge within the volume, you can see it as a current flowing across the surface. Clear? You know that? Okay. So let's try to figure out the continuity equation. Okay, let's start with this equation. Like this, phi it's equal to 0. Clear? So how you figure out the continuity equation? You have done it with the Schrodinger equation. Clear? So any idea? So you take its conjugate. Let's call this as equation first. Take its conjugate. Okay, like this thing for the conjugate variable. Okay, so now let's multiply this by, okay, you multiply this by 5 star and you multiply this by 5 and subtract the 2. So which implies like this thing, 5 star, this box operator, m square c square by h cross square 5 minus this 5 h cross square 5 star, that's equal to 0. Clear? So now you can see you are having this 5 star, this objective 5, it is same as this thing. Clear? So this object is same as this objective. So there is no problem. So they can cancel out. So this term cancels with this term. Okay. So what you get this 5 star box operator 5 minus 5 box operator 5 star, that's equal to 0. Okay. So now let's do this a bit. So it is 5 star. So it is partial mu 5 minus 5 partial mu 5 star. Okay. So let's take. So it will be like this thing. If I take one common, it's not common. It's, you need to apply it, and you will get the above equation back. So I can write this equation in this form. Okay, now let's check it. So let's check it. So do the differentiation by product rule. So this partial mu, you will be having first partial mu 5 star and then this term plus 5 star partial mu 5. So that is this very term, is it? And in this very term, you will be having partial mu 5 and partial mu 5 star with a minus sign. That will cancel with the first term, and then you will be having 5 partial mu 5 star. It is this very term. Clear? Got it? Okay. So let's since this is in the compact form, so let's put it in the component form. Clear? So what is partial mu? Since this is a contracted index, so how I will write it? So it is partial. It is like this thing. So you are having this partial mu something and partial mu and something. How you write it? So you will put it as a partial 0, and then plus partial I dash dash, partial I dash dash. Clear? Because there is a some more mu index. So how you will put it? So you will let me write it. So step by step. So it's partial 0 5 minus 5 partial 0 5 star. Okay, plus. So you will be having partial I 5 star partial I 5 minus 5 partial I 5 star. That's equal to 0. There is a sum over I 1 2 3 or x y z. Clear? It is a special index. Okay, so what is partial 0? It's 1 by c partial by partial d. So what is it? 5 star 1 by c partial 5 by partial d minus 5 1 by c partial 5 star by partial d. Okay? Clear? Okay. So then plus what this is. So now this is nebula, is it? Partial I is nebula, but partial I upper is a minus nebula. Clear? So if you remember, so we wrote this partial mu as 1 by c partial by partial d. Okay? Then nebula. Clear? And partial mu, so it is 1 by c partial by partial d minus nebula. Clear? So it will be, okay, it is nebula. Since it's a I and I, there is some of this index, it means it's a divergence. Clear? It's a dot product between these two operators, del and del. Clear? Okay, so I will write del dot of 5 star. So I will write minus nebula 5 minus 5 minus nebula 5 star. So that's equal to 0. Okay? So let's write it. So which implies you are having partial by partial t. So I'll write it as 1 by c square phi star partial phi by partial t minus phi partial phi star by partial t. Okay? Then what you can write, this divergence of this very object. Okay? Let's put it. So it is minus times. Okay, let me write it. Minus times phi star nebula phi minus phi nebula phi star. Okay? So this is equal to 0. Clear? So what if you see, this is partial rho by partial t plus del dot j is equal to 0. It was actually apparently here, if you see, you can have partial mu, you can call this as a 4 vector j mu, partial mu j mu is equal to 0. That's the conservation law. Clear? So continuity equation gives you the conservation law. Conservation of what? Conservation of the charge. If you are having, in electrostatics, if you are having a continuity equation, that will give you the conservation of the charge. Okay? So in Schrodinger equation, the continuity equation will give you the conservation of the probabilities. Clear? Okay, here it's because we are dealing with the quantum wave equation, so it should also yield me the conservation of the probabilities. Okay, or it should okay, so that gives you the interpretation of the probability. Okay, so now let's multiply this by, so that to get the dimensions correct, let's multiply this by IH cross by 2m. Okay, so let's multiply this equation by this very equation, so that to get the correct dimensions of the factors, what is here and what is here, you will see in a moment. Okay, so what you are having, therefore I can write this as partial by partial t. So let me call this as a rho. Okay, plus let me call this as a del dot j is equal to 0, where this rho is equal to, since I have multiplied IH cross, so it is IH cross by 2m, there is c square already sitting, so you are having this phi star partial phi by partial t minus phi partial phi star by partial t. Okay, and what is j? So anybody? What is j? So it is IH cross by 2m with a negative sign, so it's minus IH cross by 2m and phi star nebula phi minus phi nebula phi star. Okay, so rho represents the probability density and j gives you the current density. Clear? So it gives you the probability flow across the surface. You can choose, let's say, some surface. Okay, within this very surface, what the probability is changing, and you look at the flux across this very surface. Okay, j gives you that kind of flux, and you represent that flux by the current. Clear? Got it? Now let's try to, in fact, have we, does this equation really yield you the correct probability or not? Okay? Now one more point to this. Okay, so let me rewrite it in a more compact form. So let's define a current 4 vector j mu as c times rho and this vector j. Clear? Got it? So that's actually equal to the j0 component and the vector j. So what this will yield me? J0 will be simply equal to, so what is J0? That is simply IH cross by twice MC and phi star partial phi by partial t minus phi partial t, and J is same. Okay? So then I can write, then this continuity equation as, anybody? Partial mu j mu is equal to. Okay, so this is the continuity equation in 4-dimensional form. Okay, so now let's look at this rho. Let's look at this variable. Now let's compare it with the Schrodinger equation. Okay, so in case of the Schrodinger equation, what is your rho? Probability density. That's simply phi star phi. Clear? Is that true? So what is the probability density in Schrodinger equation? Psi star psi. So let me write in as a phi star phi. Clear? Okay. So the current density is same thing. In Schrodinger equation, you are having the same kind of current density, minus I stars by 2m. Okay, that's actually H stars by twice Im. Phi star nebula phi minus. You are having the same kind of current in Schrodinger equation as well as here in Klein Gorden equation. There is no change at all. But what is changing only? So you are having rho this thing, and you are having rho here. Now look at this very rho. This is a positive definite quantity. Is it? So probability density is always what? It's a positive quantity. Okay? So once you calculate the probabilities from here, it's always normalized. So you can get probabilities from 0 to 1. Clear? Now let's look at this very quantity. So this probability depends upon the derivative. Clear? So let's calculate the probability, this rho for our free wave solution, free particle solution. Clear? So let's try to figure out it first, then you will see what are the problems. So what is our phi? It's a e raised power, let's write I et minus p dot x by h dot. Clear? Okay? Got it? And while E is the energy solution, huh? Okay. So I'll write it. Okay. Let's write. So now let's calculate the rho. So you need to calculate this partial phi by partial d. What it will bring me? It will bring me E, is it? So similarly, what this will give me? Minus IE, is it? So minus and minus is plus. Clear? Shall I write directly? Shall I write directly the result? So what you will get? You will get this plus minus. Okay, so this EP by twice. Okay, let me write the formula directly the result. Okay, so this is the probability density. Okay, where is the problem? For positive energy solutions, you get the positive probability density. Clear? So, but for negative energy, what you are getting? Negative energy density. Okay. This object is okay. So I should have put it. It is as EP here because EP contains both the values. Or you can write it as in this way. Let me put it this way. This P naught, and X. That is C. Simply. Yeah. So it's like if anybody is having confusion, it's like this thing. I P mu. Okay? Because now in this P mu you are having this P naught. P naught contains both the possibilities. So you get actually the probability density as negative. So which is an unphysical result. Okay? Why it is happening? So it comes all because of the second order nature of the differential equation. You are having both second order derivatives in time as well as second order derivatives in second order derivatives in space will not affect you might, but only the second order derivatives in time will affect you. Why? Okay, so let's say let's talk about the Schrodinger equation first. Okay, so Schrodinger equation contains first order time derivative and second order space derivative. What I require, let's say you start with an initial wave function. Clear? So what you need to know, only the initial condition, what is the wave function at the initial time, then you can calculate the derivatives of phi. Clear? But in case of the Klein Gorden equation, it is a second order derivative in time. So what are the initial conditions you require? You require the knowledge of both phi as well as the first derivative of phi, first time derivative of phi. Then you can calculate the second order derivative, is it? So as a solution, if you try to figure out in a given situation what is the solution, so you start with certain initial conditions that will depend on what? Both the phi as well as the second order, first time derivative of phi. Clear? And that is exactly happening in this very probabilities. So you require the knowledge of these derivatives of phi, which yields you the negative these probabilities. Clear? Got it? So that means negative energy solutions has a consequence of giving you the negative probability density in case of this kind of equation. Okay? Now you can say let's restrict ourselves to only positive energy solutions. Okay?
So let's discard by hand these negative energy solutions, and let's only work with what? Positive energy solution. That is also a well defined argument, clear? But the argument is flawed in this way. Now let's say if you are doing the perturbation theory, okay, let's simple perturbation theory. Okay, you start with some state, clear? Let's say you start with some state psi naught, and let's put the corrections to this very state in perturbation. Okay, so how you do? Okay, so I am trying to discard what? Negative energy solution, and I am working only with what? Positive energy solution. So my Hilbert space contains only the positive energy solution. The Hilbert space of a given problem is equipped with what? Completeness condition, is it? And the completeness condition gives you a set of all the possible states. Okay, so let me give you the idea. So let's say if you are having some Hilbert space defined by the energy eigenstates of some Hamiltonian. Okay, let's call these n. So the completeness condition is like this thing. Okay, so it will go from all the possible states in this very Hilbert space. Clear? Got it? So whether these are positive solutions or the negative energy solutions, whatsoever. So let's think of the hydrogen atom. So it will be all the possible states from n equal to 1 to infinity. Is it?
Yes,
all the possible energy states, they will form you the completeness condition. Clear? Or in case of the harmonic oscillator, so it will be all from what? N is equal to 1 to infinity. Is it? So all the possible energy states. Now since I am restricting my Hilbert space to only one part, okay, so you are having only positive solutions here. Let's take you are having only positive and you are discarding what? And negative. So you discard this thing. So you are taking half of the Hilbert space. Clear? So now let's say you are having certain situation where you are trying to calculate the corrections to the ground state of the problem. Clear? Let's take out the perturbation theory, simple perturbation theory. Okay, you start with the ground state and let's calculate the first order correction. Okay, what is the first order correction? How you calculate it? So energy correction will be like this thing. Okay, so NHI, if you remember the perturbation theory. What is the correction to the wave function? So what is the correction? So that is that summation. Okay, so then you put a completeness condition. Okay, let's say you are having n, let me write some k, hi, and then you are having n, then this k, clear? And n is not equal to a divided by en naught minus en k, ek naught. Okay, so how you got it? You have actually plugged in this completeness condition k, clear? So while you are trying to figure out what is the correction to the first, the first order correction to the wave function, you are actually inserting a completeness condition, is it? So, but since I have restricted Hilbert space to positive energy solutions, but the completeness condition violates that, is it? So it automatically, the negative part automatically pops out, is it? Because completeness, once you introduce a completeness condition, you need to take into account all the possible states, is it? So that it becomes one. So this object becomes equal to identity, is it? So if you take this, so this does not form the complete set of states. So the complete set of states is formed by both positive as well as negative energy solution. Even if you start with discarding the, let's say, negative energy solution in your theory, but practically you will not be able to do so. Clear? So because these negative energy solutions will automatically get popped out, or they will be generated in a given situation. Clear? So you can't get rid of these kind of solutions. Okay? Got it? Okay, so we are having two problems here with this wave equation. What are the problems?
Negative solution.
So you are having negative energy solutions, and second is okay, probability. There is no well-defined probability density corresponding to this thing. Okay? Okay, so these are the historical developments. Okay, now let's try to figure out what is the non-relativist limit of this very equation. Okay? Then we'll summarize what we have done. Any question? structure. Okay, so here will be the home assignment. You will see, let's say, if you are having a relativist particle that is tunneling through some barrier, potential barrier, okay? So you are having a relativist free particle that is tunneling through this barrier, okay? So you are supposed to do that, calculate the so let me write, there is a, so this will be home assignment. Try to understand this thing, Klein paradox. So you are having a relativist particle, okay? The way you are doing the tunneling problems in simple quantum mechanics, a particle tunnels through a potential barrier, okay? You need to calculate the same thing here, okay? So you will have to calculate what is the transmission probability for a relativist particle that satisfies the Klein Gorden equation, okay? You will say actually transmission probability overshoots 1, okay? So usually transmission probability should be what? It's either no transmission or the complete transmission. It is from 0 to 1. Clear? You got my point? If you are having transmission probability 1, that means there is no reflection at the barrier. Clear? Everything gets transmitted. Now if you are having transmission less than 1, that means something has been reflected at the barrier. Clear? Now if you are having transmission more than 1 and you are having some reflection at the barrier as well, something is wrong, is it? So try to understand this kind of paradox. So this will be the home assignment for this week, okay? So you have to do this thing, okay? I will look at it in the next week, okay? So just do this kind of assignment. Now let's look at the non-related limit. Okay, what I will do, let's make an assumption, okay, that this phi, okay, RT, so this is equal to some psi of RT e raised power minus I mc square t by h plus. Okay, while I have actually, so this psi does not contain rest mass energy, I have taken it out. Clear? When I take the rest, okay, non-relativist limit, so that means the total energy, what? If you subtract the rest mass energy, okay, so what it means, let's say you are having total energy E and you subtract the rest mass energy, okay, so this object is very less than what? E, is it? So this difference is very small. So what it is? So you call this as, let's write it as E prime, so you usually call it as a kinetic energy. Because kinetic energy is very smaller than the rest mass energy. Okay? Is that true? So is this the non-relativist limit? The other way to think of this limit is, in non-relativist mechanics, what is the velocity of light? It's infinity. Is that true? So in relativity, velocity is limited by c, is it?
Yes, sir.
But in without relativity, what is the bound on velocity? It can be anything. Clear?
Yes.
So that means the velocity of light c is infinity. Clear? Okay, so let's start. I will do that way. So then you will understand it. Okay, so this is very easier to do. So what I have done, I have started with an assumption that our wave function is like this thing, such that I have separated out what? The rest mass energy, because it is a very huge quantity. Clear? Okay, so now let's substitute it in the Klein Gorden equation. You are having 1 by c square, partial 2 by partial d2. Okay, so let's substitute. So you are having phi minus nebula square phi, that's equal to minus m square c square divided by h plus square phi. Clear? So let's substitute it here. Okay? Clear? Now what is phi? Okay, so let's calculate this partial by partial t of phi. So let's calculate it first. So what that is? Partial by partial t psi e raised power minus I mc square by h plus t. Okay? So what is that? So it is partial psi by partial t e raised power minus I mc square by h plus t minus I mc square by h plus psi e raised power minus I mc square by h trans t. Clear? So now let's take the second derivative, partial 2 by, so what is that equal to? So it is partial 2 psi by partial t2 e raised power minus I mc square by h trans t, then plus partial psi by partial t. Here you will get I mc square by h trans e raised power minus I mc square t by h trans. Okay, then you are having this very term minus I mc square by h trans partial psi by partial t e raised power minus I mc square t by h trans. Okay, then you are having again, so you need to differentiate this thing. So this will come down minus and minus. Okay, so it is minus. Okay, so it is minus. Okay, mc square by h trans square whole square. Okay, psi e raised power minus I mc square t by. Clear? So how much is that? Okay, so therefore this 1 by c square partial t. So this very thing, okay, minus nabla square 5, it is equal to, tell me. So how much is that? So you are having, so this is equal to, okay, 1 by c square partial t, so now to partial 2 psi by partial t2, is it? So let's take exponential out. So if you see this and this term, they are same. So you are having, okay, like this thing, minus twice I mc square by h trans, then partial psi by partial t. Okay, then you are having one more term there, minus m, okay, square c raised power 4 divided by extra square. So it should be extra square. Extra square here. It is extra square. Okay. Then you are having this side. Okay. E raised power minus I mc square t by extra. Okay. Then you are having minus lambda square. So it is simply e raised power minus I mc square by extra t lambda square acting on side. Okay. Because this does not contain what? Okay, so this is equal to what? M minus m square c square divided by h square psi e raised power minus I mc square t by h plus. Okay, so this object. Clear? Huh? Any problem? Okay, so now let's look at. So you are having 1 by c square here. You are having c raised power 4 here, is it? So it is m square c square by h square. It is same thing as this thing. Clear? So that means this very object cancels it. This very object. What remains there? So which implies 1 by c square partial 2 psi. We are doing exact calculation till now, so there is no problem. So c square is here, this c square is here. It is twice I m by h trans partial psi by partial t. Okay. So then it is equal to, let's take this on the other side. So it is equal to nabla square psi. Okay. Clear? So exponentials are cancelled. Okay? Huh? So no, c square is divided only with this time derivatives. Clear? There is no c square here. Okay? Any problem? Now let's take the non-relative limit. So c tends to infinity, is it? So that means when c is large, so this very goes. Huh? So this is very small. Clear? So non-relative limit means c tends to infinity. So it means this term goes. Okay? So in this very case, so which implies you are having, let me multiply, okay, twice I m by h trans partial psi by partial t minus nabla square psi. This is actually Schrodinger equation. So let me rewrite it. So it is something. So let's write I h trans divide. Okay, so you are having 2m by h trans square, like this thing, partial psi by is equal to minus nabla square psi. So what it gives me? I h cross partial psi by partial is equal to minus h cross square by 2m nebula square. So this is the non-relative limit of Klein Gorden equation. That is the Schrodinger equation for free particle. Clear? So this is actually the Schrodinger derived actually non-relative limit. So he stuck with what? The non-relative limit. Okay. So it was later on actually the Klein and Gorden who reformulated this theory. Okay. For free particle there is no potential. That's why there is no potential. Clear? Got it? Ultimately is with this thing. Right? Okay. So any question till now? So I am just doing till now the wave equations. Okay. So I am just doing the historical development. Clear? So I will come to this point. What is the interpretation of these negative energies? Okay. So we will see it. Okay. So we'll see once we try to quantize fields, these negative energy solutions go, and they have a interpretation. Okay. So we'll see how to interpret these negative energy solutions. Okay. It was actually Dirac who proposed a kind of theory to avoid these negative energy solutions, but only for fermions. So that was not applicable to the bosons. Okay. So you need to actually invent certain things to arrive at the conclusion what negative energy means. Okay. So we'll see. We'll go step by step. No problem.